Hi everyone. The point of today's video is to serve as kind of a halfway point and as kind of a summary of what we've done so far. We've gotten to the point where we've defined what work is, we've defined all four types of energy we're going to use, and we've started to kind of mix those together. Now, what we're going to do from here on out is show how work and energy are related. In other words, if work is done, how does that affect the types of energy that an object or system has? So to start, we're just going to create kind of a flow chart that shows how you can classify different types of energy. Some of the different types we've talked about include kinetic energy, which is the energy associated with an object that's moving, gravitational potential energy, which is energy associated with some object being up above some other more massive object, such as something being held up above Earth's surface, elastic or spring potential energy, which is energy associated with compressing or stretching or otherwise deforming some object. And all three of those types of energy fit under the umbrella of what we call mechanical energy. It's very easy to convert from one type of mechanical energy to the next. You throw a ball up, it loses kinetic energy, it gains gravitational potential energy as it comes back down, vice versa. You have a cart that that's going on a track and it hits like a spring bumper. As it compresses the spring, it stores elastic potential energy, loses kinetic energy. As the spring pushes it back out, the reverse happens. The only other type of energy is not mechanical energy, but it's called internal energy. This is energy associated with friction. It's energy loss. You lose mechanical energy due to friction, but that energy doesn't just disappear, it gets turned into internal energy. So there's a little flow chart that shows how the different types of energy break up. What we're going to talk about today and what we're going to work on is called the work energy theorem, and it goes something like this. If positive net work is done by an outside force, I'm going to underline that, the total energy of a system will increase. If positive net work is done by an outside force, the total energy of a system will increase. Okay, so if work is done, the energy changes of the system. Now, I'm going to come back to that definition of outside force in a second, but I'm going to show you what this means or how this looks on the reference table. This equation right down here where we see W equals FD, that was like our first look at work and what it does and how to calculate it. But notice this other part of the equation, work equals change in total energy. That's the definition of work we've been using the whole time. Work is associated with a change in energy. Work equals delta ET. ET stands for total energy, and the equation right below that is ET equals potential energy plus kinetic energy plus Q. By the way, they're combining the two types of potential energy there. So taking these two equations together, we kind of see their meaning. What am I doing? We see that work changes the total energy of a system, and the total energy is just the sum of all the types of energy that are present in the system. If there's an object in the system that has kinetic energy, that gets thrown in. If there's any type of potential energy, that's included, as well as internal energy. Work involves changing one or all of those types of energy. Let's go back to outside force for a second, though. What we mean by work done by an outside force, we're talking about three very specific forces. What we mean by that is the applied force, tension, and the normal force. If work is done, if positive work is done by any of these three types of forces, the total energy of a system will increase. ET will increase. We're not just saying one increases and the other decreases, we're saying the total energy will increase. Also, if negative work is done by one of these forces, the total energy of a system decreases. Now you might be thinking, well, wait a sec, doesn't that leave out a whole bunch of forces? Like, what about the force of gravity? What about friction? What about the spring force? If they do work, why doesn't that change the total energy? And it turns out that, interestingly, they are actually already accounted for. Let me explain why. If gravity does work on an object, okay, it can definitely change some type of energy, but gravity already has a specific type of energy associated with it. Gravity is already associated with gravitational potential energy. So if the force of gravity does work, that changes PEG. If friction does work on an object, that changes Q, and that's already accounted for in our total energy equation. And if the spring force does work on an object, that's again accounted for as one of the types of potential energy, elastic or spring potential energy. So these three forces, the work that they do is already built in because we have specific energy terms to account for that. The applied force, tension, and normal force, if you think about it, the only type of energy that those forces can give to something is kinetic energy. They go into increasing the kinetic energy of an object. So, if you're trying to figure out if positive net work is done on a system, you got to look to see if one of these forces is doing work. If that is true, then you know that work is being done and the total energy will change. These forces can do work as well, but it means it's going to change very specifically one of the potential energies or the internal energy. Okay? This will come back around. This definition will come back around when we start talking about conservation of energy. But for right now, I'm just going to leave it. Okay? The outside forces that can change the total energy are the applied force, tension, and normal force. These forces, if it's just these forces doing work, then the total energy isn't changing. You're just changing one of the types of energy, either the potential energies or the internal energy. Let's get to some examples. We're not going to calculate in these examples right away. First, we're going to figure out that if work is being done, what type of energy is changing. That's the first thing we're going to figure out. A 1,200 kilogram car moving at 8 meters per second has 2 times 10 to the 5th joules of work done on it. What is the car's new speed? Okay, so we have a car, it's moving, so it already has kinetic energy, then it has work done on it. It doesn't say what force does the work, but that's okay. What's the car's new speed? If it's implying the speed is changing, that's implying the kinetic energy is changing. So in this case, remember that as we do these problems, we are going to need to determine the type of energy that changes. And in this case, that is kinetic energy. So, instead of writing work done equals change in total energy and then writing out change in kinetic energy plus change in the potential energies plus change in internal energy, it doesn't say anything about this car moving up. Okay, it doesn't say anything about this car moving up to a higher elevation, so no change in gravitational potential energy. It doesn't say anything about any sort of springs, so no change in elastic potential energy. And it doesn't say anything about friction, so no change in internal energy. I'm just going to write this. I'm going to write down the work that's done on this car goes into changing the kinetic energy. See how I did that? I know that there's work done, and I thought, okay, what type of energy is changing? It's asking about the car's new speed. That's implying that the kinetic energy is changing. I could expand this out to, instead of delta KE, writing KEF minus KEI, final kinetic energy minus initial kinetic energy. And I could go one step further by writing that the work done is equal to 1/2 mVF squared minus 1/2 mVI squared. Now I can just plug in. The work done, 2 times 10 to the 5th joules, that's how much work is done, equals 1/2 of the mass of the car, 1,200 kilograms. We're looking for the final speed, so VF squared, minus 1/2, 1,200 kilograms. The initial speed is 8 meters per second squared. Now it's just time to do some math. 2 times 10 to the 5th is 200,000. This would, let's see, half of 1,200 is 600 VF squared minus 600 times 8 times 8, which is 38,400. I'm going to add this to the other side, divide by 600, and take the square root. Final velocity of the car is 19.93 meters per second. We didn't have enough information to solve that using forces, I don't think. We didn't have enough information to solve it using kinematics, but we were able to figure out the final speed of the car by simply by using the idea that work changes some type of energy. The work done changes the energy of the car. Next question. 20 joules of work is done to lift a mass from the ground straight up to a height of 2.5 meters. What is the mass's final potential energy? So again, what type of energy is changing here? You might be tempted to say kinetic energy is changing because you have to move the mass, and that might be true, but it doesn't say that the kinetic energy is changing, and besides, you could even make the argument that when the object's on the ground, it's got no kinetic energy. When it's being held at 2.5 meters, it's also got no kinetic energy. So we don't really have enough information to say what happens with the kinetic energy. That's not the focus of the problem. The focus of the problem is this object moves up, and therefore the gravitational potential energy changes. So the work that's done goes into changing the gravitational potential energy, which means we must have the final gravitational potential energy minus the initial gravitational potential energy. The mass starts on the ground. Any object on the ground has no gravitational potential energy. So I'm just going to cross this off and write 0, and we're left with this. The work done is equal to the final gravitational potential energy. Well, we know the work done is 20 joules, and we're looking for the final gravitational potential energy. We're done with the problem. Sometimes it's really just as easy as that. It makes sense. We already had a height, but we weren't told what the mass is. We could actually go back and figure out what the mass of the object is, by the way. But we were told that we assumed that the initial gravitational potential energy was 0, and then some work was done. If you start at 0 joules of energy, and then work is done, the amount of work done is equal to the final gravitational potential energy. Kind of makes sense. So that would be 20 joules. Sometimes the questions really are that straightforward. The next question is a little bit similar. How much work is done in order to give a spring with a spring constant of 900 newtons per meter and elastic potential energy of 76 joules? So we have a spring, we're giving it some energy. Very clearly, the elastic potential energy changes. The work in this case goes into changing the elastic potential energy. We have some final elastic potential energy minus initial elastic potential energy. That would give us the change. Let's assume that the spring doesn't have any elastic potential energy to begin with. So that's 0. Again, it turns out that the work done is simply equal to the final elastic potential energy. So I just need you to be on the lookout for that. Sometimes these problems don't involve all that much math. Now this would have been different had we said that the spring was already stretched or compressed a little bit, and we want to compress it more to give it 76 joules more energy, and then we ask like how much, what's the compression of the spring. That would be a totally different case. Okay, that would take a lot more work, or pardon the pun, that would take a lot more writing and calculation on our part. But sometimes if you're asked how much work is done, and then if you're told how much work is done, you're just asked find out how much energy is stored in the system, that's your answer. Sometimes it doesn't always have to be super hard. A few more questions here. Below is a graph of force versus displacement for a golf ball being struck by a golf club. Determine the work that was done on the golf ball as well as the ball's final velocity if its mass is 0.085 kilograms. So the work done on the golf ball, you might think, okay, well, let's see how much the energy changes by. We're not told how much the energy changes by. All we have is the mass. We don't have the final velocity of the ball. Matter of fact, that's something we have to find. We don't know anything about how high the ball goes. So using the work energy theorem here isn't going to work out very well. However, we are given a graph which shows the force on the ball and its displacement. So in other words, here's the force of the club hitting the ball, and here's the displacement over which that happened. So we could calculate the work by simply doing this. We know that the work done by the club equals the force of the club times the displacement times cosine theta. If you ever played golf before, you know that the force from the club on the ball is going to be in the same direction as the ball's displacement. Therefore, the angle between those two vectors is 0, and the cosine of 0, as we know, is 1. The force from the club is a constant 6,000 newtons, and the displacement while the club is striking the ball is 0.05 meters. The work done is equal to 300 joules. Okay, so we found the work using this graph. As a matter of fact, I want you to take a closer look at this graph. Okay, what would you have done differently if I told you to find the area under the curve here? You would have said that this is a rectangular shape. You would have said that the base is 0.05 meters and the height is 6,000 newtons. Wait a sec, and then multiplied them together. That's the exact thing that we did here. What I'm trying to show you is that you always need to be on the lookout for graphs. Okay? A lot of times the slope is useful for a graph. This is not one of those times. If you take a force and divide by a displacement, that's not getting you anything. However, when you find an area, that means you're taking the y-axis and multiplying by the x-axis in some fashion. And in this case, force multiplied by displacement is equal to the work done. So we're going to write this off to the side. For a F versus D graph, the area under the curve is equal to the work done. For a force versus displacement graph, the area under the curve here is equal to how much work is done. That's a good fact to remember. Okay, it can save you some work, or it can save you some effort. That would be even more crucial to know if we had a force that was changing as the displacement changed, and that would be more realistic. If we had that, we couldn't just rely on this equation. We would have to make an area calculation in order to figure out how much work is done. Okay, so we have the work done on the ball. We know that the golf ball was sitting at rest at first, and then it started moving. So clearly the work went into changing the kinetic energy of the golf ball. The initial kinetic energy of the golf ball was 0, so the work must be equal to 1/2 mvf squared. 300 joules is the work done. 1/2 mass of the ball, 0.085 kilograms, times vf squared. We solve for vf, the final velocity, divide by half, divide by 0.085, and we take the square root. We see that the ball has a speed of 84 meters per second after being hit. Okay. Now, could we have found that using kinematics? Yeah, we could have, and we would get the exact same answer. It's interesting that this also allows us to get the same answer. Again, in some cases, we have a little bit of an option in terms of what we can do. In other cases, it's up to us. In other cases, it's up to us whether we want to, I misspoke. In some cases, it's up to us whether we want to solve using one method or another, whether we want to solve using energy or using forces and kinematics. In other cases, we're kind of restricted to solving with one particular method. 3 more examples. First one, force of friction on an 88 kilogram skier skidding to a stop is 350 newtons. If the skier comes to a stop in 11 meters, how fast were they moving initially? So let's think about how the energy is changing for this skier. The skier is coming to a stop, so we know that the kinetic energy is decreasing. Now, you might want to say something like, well, hold on a sec, where's that energy going? Doesn't it have to go somewhere? It is true that that energy is going somewhere. The energy is being transferred or turned into internal energy, because what's stopping the skier? The force of friction. I don't need a parentheses there. But we, in this case, can consider the force of friction to be an internal force because the energy stays with the object, with our object being the skier. Okay. So, There's a couple different ways that we could do this, and this problem would actually work a little bit better if in our conservation of energy topic, but we can still do it right here. We're going to talk about how the kinetic energy changes, and again, what force causes the kinetic energy to change. It's the work done. It's the force of friction. So let's find the work done by the force of friction. That's going to be equal to the change in kinetic energy. The amount of work done by friction is equal to the change in the kinetic energy. We know the force of friction, or the work done by the force of friction, equals the force of friction itself times the displacement times cosine of theta. And we know delta Ke can be replaced by Ke final minus Ke initial. We know if the skier is stopping, that the skier is moving forward, the force of friction points backward. That means that there's 180 degrees between those two vectors. Cosine of 180 degrees is -1. So I'm down to negative Ff, force of friction, times displacement. There is no final kinetic energy because the skier comes to a stop, which leaves us with minus initial kinetic energy, which is 1/2 mvi squared. Notice I have a negative on both sides of the equation. I can just change those to positive signs. If I'm looking for vi, then I have the force of friction, I have the displacement, and I have the mass. I have everything I need to solve. 350 newtons times a displacement of 11 meters, 1/2, 88 kilograms, vi squared. I'm going to multiply 350 times 11. Half of 88 is 44. Divide by 44 and take the square root. The initial speed of the skier, if 350 newtons was sufficient to stop them in 11 meters and the skier's mass was 88 kilograms, the initial speed was 9.35 meters per second. Again, that's another one. You could solve this using kinematics and forces. It's really up to you how you want to do it. A boy does 3 joules of work in pulling back a 0.04 kilogram rubber band. So we've all done this before. How fast will the rubber band move once he releases it? So this actually kind of has 2 different steps. As the boy pulls back the rubber band, he's applying a force over a displacement. He's doing work. What type of energy is going up for the rubber band? Initially, the elastic potential energy increases. Okay? Energy is being stored in that rubber band because work is being done by the boy. But as soon as the boy shoots the rubber band, as soon as he lets go, the rubber band starts to unstrap. It starts to go back to its normal length. That means the elastic potential energy goes down, but it's got to go somewhere. Where does it go? Well, the rubber band's going to go flying across the room, so clearly it wasn't moving before, and now it's moving. The elastic potential energy did increase, but then it is converted to kinetic energy. So we're going to do kind of a sequence of this. The work done by the boy goes into changing the elastic potential energy, which ultimately goes into giving the rubber band some kinetic energy. Let's just focus on the first part. Initially, the rubber band probably wasn't stretched, so the work that was done, which is 3 joules, that 3 joules of energy is equal to the final elastic potential energy. That's how much potential energy was stored. But then, if all of the final elastic potential energy gets turned into kinetic energy, we could write something like this. PESF is equal to the change in kinetic energy. There was no initial kinetic energy, so this can turn into 0. What we see is that that work that was initially done and put into the elastic potential energy of the rubber band is now being transferred to kinetic energy. So that 3 joules that was initially going into the stretching to increasing the elastic potential energy is now 3 joules of kinetic energy once the rubber band is released and unstretches and goes flying across the room. And we see in this case, the rubber band would move once it's unstretched at 12.25 meters per second. Okay, so again, there's some complex things that can happen. There's lots of energy changing places. I think it's just as important to be able to identify how the energy changes as it is to figure out exactly, to do a calculation, to figure out how fast the object is moving. If you can't do this, then you can't do this stuff down here. This is just as important. Last example. 100 joules of work is done as a 3-kilogram cart is pulled a distance of 5 meters up a ramp, and the ramp is inclined at 30 degrees. How much of that work was done to overcome friction? Anytime you see this, the question that is being asked is really how much internal energy was generated. That's really what's being asked, okay? If work is done to overcome friction, you're being asked to find Q, all right? How much of that work was done to overcome friction? Basically, how much internal energy is there in the system? In this case, we have an object going up a ramp. It goes 5 meters along the ramp. It doesn't say it goes 5 meters in the air. It goes 5 meters along the ramp, and the ramp's angle is 30 degrees. Clearly, we know that we're going to have to calculate Q, so Q must be changing. But there's another type of energy that changes. Again, you might be able to argue that possibly the kinetic energy is changing, but perhaps this object is getting pulled up at a constant velocity. You don't know that the kinetic energy is changing. There's no sense in including it. However, you do know that the gravitational potential energy is changing. You know this because the object goes up. You need to figure out how high it goes up. If you think about a ramp, you know that we have a right triangle here. We are looking for the height that the object moves up if it goes 5 meters up the ramp. Based on the angle we were given, that's the opposite side. This is the hypotenuse. This is a trig question. Opposite and hypotenuse are associated with sine. So we use the sine of 30 degrees is equal to the opposite side over the hypotenuse, which is 5 meters. To solve for x, we end up doing 5 meters times the sine of 30 degrees. X is 2.5 meters. That is the change in height, or in other words, the final height. You could say that the initial height is 0. So now that we have some information about, the height, we can talk about how the work done, because the cart's getting pulled, work is being done, how that changes these types of energy. If both of these change, we have to include both. The work done is equal to the change in gravitational potential energy plus any internal energy that gets generated. I don't need a delta in front of Q because we always kind of assume Q starts at 0. Okay? This is totally fine. Work that's being done can change 2 types of energy at once. Nothing wrong with that. So the work done equals PEGF minus PEGI plus Q. That's from the delta. There was no initial gravitational potential energy, so the work that gets done goes into increasing the gravitational potential energy and the internal energy. Gravitational potential energy is given by mgHf plus Q. Now we simply plug in. We know that 100 joules of work was done. The mass of this cart is 3 kilograms. Acceleration due to gravity is 9.81 meters per second squared. The final height that the cart gets to is 2.5 meters. And Q is what we're looking for. If there was no friction, then all of the energy would go into changing the gravitational potential energy. And that actually means the cart would get up higher. Because there's friction, some of the energy needs to go into overcoming friction. And therefore, once friction is overcome, that energy is now internal energy. That's what we're looking for here. Solving for Q means multiplying these together and subtracting from 100. So 100 minus, in parentheses, 3 times 9.81 times 2.5, and the parentheses, 73.575. Subtract that from 100. There is 26.425 joules of internal energy that was generated. Okay? A lot of these work questions that are more complicated than just calculate how much work is done or calculate how much energy there is if in these conditions. A lot of these questions can get a little bit complex, and when we do conservation of energy, you'll see that they continue to get a little bit more and more complex. All we're trying to do right now is we're just trying to show the relationship between work and energy. If you start off by always thinking about, okay, is work done? And if it is, then what type of energy changes will put you on the right path? We'll talk about conservation of energy next time. I'll see you later.